This is the solutions to Thursday, June 11th of June 2015 paper, which was used for the mock exam for students in January 2016. The code is 6PH0401. So if we start off with the multiple choice, the first question is what is the number of neutrons in this nucleus here? Well, the bottom number is the proton number, so that's the number of protons. Top number is known as the nucleon number. If you remember, that's the sum of the number of protons plus the number of neutrons. So in this case, there's 238 is the sum of the number of protons and neutrons, but 92 protons. So the number of neutrons must be just 238 minus 92, which is 146. So that was B. Next one down is asking us which one of these is correct. Well, if you work your way through, you can check each individual one. So mv squared divided by 2, if that was equal to momentum squared p squared, let's call it p instead of rho, then momentum is mv, so that would be equal to mv squared, which is m squared v squared. But mv squared divided by 2 is not the same as m squared v squared, so no, that's not correct. And if you do a similar thing, you can pause the screen here if you like during the video. You'll see that it has to be D. So the correct answer is D. You've got to be a little bit careful here. Which one is not, that's why it's in bold, is not a valid conclusion from Rutherford's alpha scattering. Is it a valid conclusion to say the nucleus is charged? Yes, it must be, because some of the alpha particles were deflected and some of them actually deflected backwards, so that wouldn't be possible unless the nucleus is charged. So that is a valid conclusion. One of the conclusions was not, this is not the valid one. You can't say the nucleus contains protons and neutrons. That came from a later experiment. You know it's charged, but this particular, the Rutherford scattering experiment, didn't show it contained protons and neutrons. So that's from a different experiment. It is valid to say the nucleus contains most of the mass of the atom. It must have a high mass. Otherwise, instead of the alpha particles being, some of them being scattered backwards, the alpha particle, if the nucleus was quite a low mass, it would have just sort of deflected the nucleus out of the way. So the nucleus has got a high mass. So that's a similar point there. The nucleus does contain most of the mass of the atom. This last one is also true. The nucleus must be very small compared to the atom. If you had a great big nucleus, most of the alpha particles wouldn't have travelled straight through, would they? So the nucleus must be small. So that is a valid conclusion. On to number 4. Electrons are released from a heated metal filament. If you heat a metal wire, electrons are released. This process is known as, it's D, therm ionic emission. That's where the word therm comes from. Therm meaning heat. It's heat emission. Electrons are emitted, leaving behind ions, hence therm ionic emission. Don't confuse it with a photoelectric effect. That's where if you've got a metal surface and you've got light, so you can think of light as a wave or as a packet of energy, a photon, that's when electrons inside the metal surface can escape. But that's not gaining energy from heat. That's gaining energy from the electromagnetic wave or the photon. So don't go for that one there. Number 5, which of the following is a possible unit for rate of change of momentum? Well, momentum's mv, isn't it? Rate of change means with time. So that's the unit for momentum is the kilogram meter per second. So the rate of change of momentum, if we divide that by time, and then you're going to get kilogram meters per second squared, which is A. On to number 6 here. We've got a length of current carrying wire. There's our wire, look there, carrying a current, placed at a right angle to this uniform magnetic field. I've drawn it in this direction here. It says when the current in the wire is I, the force acting is F. It doesn't ask us to get the direction of the force, although you could if you wanted to with Fleming's left-hand rule. So the force on a wire of length L, where the length L is the length inside the magnetic field, flux density B, and the angle between the two being theta. Here it's at right angles, so the angle between the magnetic field and the wire is 90, and sine 90 is 1, so F equals BIL. If you double the flux density, if we increase this by a factor of 2, but we quarter the current, same as timesing it by 0.25, those two effects are going to lead to 0.5, aren't they? 2 times a quarter is 0.5, so the force is halved, which is C. That takes us on to question 7. We've got a pendulum with mass m and length of string x swinging, and it's swinging through an arc. So it's kind of like circular motion, isn't it? Or it's a little bit unusual because often in circular motion you assume the speed is constant. Here the speed isn't constant, is it? It's going to be a maximum at this point here. But if you consider that middle point there, we know the pendulum is about to move up here, so the tension must be larger than the weight. So we can write here tension larger than the weight. The resultant force, Fc, is the resultant force here. The resultant force is going to be upwards since the tension's bigger. So you can actually write the centripetal force, the force which is going to cause that sort of circular motion there, is T minus mg. Centripetal force required is always mv squared over r, where r is the radius of circular motion. In this case, the radius is fixed by the length of the string, so that's going to be x there. So we can write x here, substitute for x here, which I've done that down there. So rearranging T equals mv squared over r plus mg, and there's the x there. So that gives us option B there. Number 8, we've got an acceleration of electron in an electric field. Well, to get acceleration you need force first, don't you? Force divided by mass. And the equation on the data sheet that links force and the electric field strength is F equals EQ. So electric field strength times the charge on the electron gives us the force, and then just divide by the mass. And that gives us the acceleration there, which is D. Over to number 9 there. E equals mc squared, or you can write it in this slightly different form with the deltas, can be used to calculate what? Well, it can't be used to calculate the kinetic energy of an electron, because kinetic energy is a half mv squared and we haven't got the speed of the electron, so it's not that one. The energy produced when a lambda particle decays, well, at the back of the paper it hasn't given you the mass of the lambda particle, so it's not this one. It's C, it's the energy produced when a proton and an antiproton annihilate. If a proton and an antiproton annihilate, it produces 2 photons. What energy is released? Well, you've got a rest mass energy here, haven't you, and rest mass energy here. Equals mc squared. If you put the mass of the proton in, and remember the mass of the antiproton is the same, you can calculate the rest mass energy of the proton, which will be exactly the same as the rest mass energy of the antiproton. And then you add those two together, divide by 2, and that will give you the energy of each photon, assuming there's no kinetic energy initially. So it's C, not D. Last one then. Large Hadron Collider accelerates protons to very high energies. Why? Well, that's not to annihilate protons and antiprotons. They can annihilate if they're stationary. You don't need to accelerate them to do that. You could do, but you don't have to. That's not what the Large Hadron Collider is for. To allow protons to collide with other protons, well, you could do that at low energies. You're trying to accelerate them here, so there must be some reason why you're trying to accelerate them to collide them, and that's to create particles with a large mass. So if you are putting a lot of kinetic energy here with a big voltage, you give these particles a lot of kinetic energy, and they've got a little bit of rest mass energy as well, and if you use E equals mc squared, the mass that you could create would be the total energy of the particle divided by c squared, and the total energy of each particle is going to be the rest mass energy plus the kinetic energy. I mean, you've actually got 2 sources of rest mass energy and kinetic energy here, haven't you? But putting in a big energy will allow you to create a big mass. So it's C. It won't produce individual quarks, so that leaves us with 10C. On June 2015, 6 PH0401 Module 4, question 11, we've got this apparatus here used to demonstrate the force acting on a current carrying conductor when it's in a magnetic field. The apparatus is placed in a magnetic field, it says here. When the switch is closed, the copper rod rolls along the aluminium rods. Add to the diagram to indicate the direction of the current. So as soon as we close that switch there, current flows from positive to negative, so it's going to flow anti-clockwise there. So it said and indicate the direction of current in the copper rod. So we need an arrow down there. Let's just put I to show the current is acting down. State the direction of the magnetic field that will make the copper rod move to the right. So we want the motion to the right, therefore that means the force must be to the right. So this is Fleming's left-hand rule because we're actually providing the current here and we're not inducing the current. So it's FBI, isn't it, on the hand. So F we want acting to the right, the I is down the page there, so B, first finger needs to be into the page, so the magnetic field needs to be in to the page, so we'll just put in to the page there. It's worth 2 marks, isn't it? So we've just put an into page. Let's just read the question. State the direction of the magnetic field that will make the copper rod move to the right. It hasn't asked us to explain why, so it doesn't seem necessary to mention Fleming's left-hand rule. In which case, we seem to need more information, don't we, into the page. I think we should say into the page at right angles, so I suppose into the page could be at a slight angle, whereas we actually need it into the page at a right angle. So if we add the additional information at 90 degrees to the rod, then that clarifies things, and that probably earn us the 2nd mark there. Okay, on to question 12. We've got pions belong to a group of particles called mesons. You should know that a meson is composed of a quark and an anti-quark. It's not necessarily the same quark, like an up quark and an anti-down. An up quark and an anti-up. Could be something different, but you often denote a meson as being quark, anti-quark, like that. It tells us pions can be used as radiotherapy to treat brain tumours, and we've got a list of each of these 3 quarks here, up, down, strange, and it gives us their charge in terms of the electron charge, and it asks from the list below which could correspond to a negative pion. Well, you should know a meson is a quark and an anti-quark, so it can't be this one here, it can't be that one there, so it just leaves us to well, we know it's a negative pion, so it's got a charge there of -1 of E, so it's just a case of checking which one of these possible options would work. Well, an up quark is +2/3, so an anti-up would be -2/3, and then we'd have another -1/3 from the down, so that would give us a charge of -1. So that one seems feasible, so probably is that one, but if we just check the other one quick, an anti-strange would be +1/3, plus an up would be +2/3, so that would be +1E. So that couldn't be a negative pion there. So out of that list there, that's the only possible one there. So it asks us to circle that one there, so circle that one there for the 1 mark. This one here, it gives us the mass of the pion in this unit there, and it asks us to calculate that in kilograms. Well, there's different ways you could do that here. Each of you will use a slightly different technique. I mean, the quick technique is just to recognise that you have to take 140, where you've got the mega, that's timesing it by 10 to the 6. Where you've got E, that's timesing it by 1.6 times 10 to the -19, and then you're dividing by C squared, so divided by 3 times 10 to the 8 squared. I'm trying to video and write this at the same time, so I'm not really keeping on the lines here, but hopefully you're being neater in your presentation than I am, and that will give you a value of 2.49 times 10 to the -28 kilograms, which gets Another way of thinking about it is to write out 114 megaelectron volts over squeezed C squared. You know that's a unit of mass, don't you? Because you've got a unit of energy there and you're dividing it by c squared. Well, if you take this term here, that is the rest mass energy, 140 mega electron volts. So if you want to convert that into joules, 140 mega, and then times by 1.6, remember, times 10 to the minus 19. Remember, 1 electron volt is 1.6 times 10 to the minus 19 joules, and if you've got 140 million of these, you can work out in joules what the rest mass energy should be, and that comes to 2.24 times 10 to the minus 11 joules. That's the rest mass energy of the pion. And then you can just use m equals E over c squared, so you're just putting that into there. You've got the rest mass energy in joules now. Remember, you always have to use joules when you calculate, and so the mass is just going to be the energy there, rest mass energy, divided by 3 times 10 to the 8 squared, and it gives you the same answer as before, 2.49 times 10 to the minus 28 kilograms. They're both giving you the same answer. The only thing is here, at least you appreciate why you're doing what you're doing. You're recognising that that figure at the front, if you literally just ignore the c squared, is the rest mass energy. Okay, on to question 13. We've got a picture of a roundabout in a child's playground. We've got a child, mass 20 kilograms, sits on the roundabout without holding the bars. So I'm going to draw a little picture from above there. I'm just thinking this out myself. There's the centre of the roundabout, there's the child. You've got a distance between the centre of the roundabout and the child, 0.8 metres, and it tells you the maximum frictional force is 35% of the weight of the child. Calculate the minimum time taken for one revolution if the child is not to slide off. Well, you probably know yourself that if you spin a roundabout round too fast, if you're sat on, or even if you're holding the bars, it's very difficult to stay on. So we're calculating the minimum time. Now it says the maximum frictional force, because friction reaches a maximum, doesn't it? If you've got something sat on a surface and you tip it, as you tip it progressively more and more, the frictional force increases until it reaches a maximum, and then if the weight force pulling down exceeds the maximum, it will just slide off. So let's have a think about what's going on then. So this child's in circular motion going around and around, so let's just redraw the child there like that. So if the roundabout was rotating in that direction there must be some kind of centripetal force acting down to keep that child moving around with the roundabout. So what's the source there of that centripetal force? Well, it's friction. So the centripetal, if I put FC, centripetal force, the centripetal force is provided purely by friction between the child and the roundabout. They're not holding onto the bars or anything like that. So the centripetal force is solely due to the friction. It's not a resultant force in this case. It's just the centripetal force is solely provided by the friction. So the centripetal force required in motion is always mv squared over r. So the centripetal force required is coming from the friction. Now, as the roundabout spins faster and faster, the friction increases and increases and increases, and it provides the centripetal force needed. But if you go too fast and this becomes too big, if that exceeds the maximum friction, then the child's going to slide off. So the maximum velocity, you can determine it by setting this equal to the maximum friction there. And that'll be the maximum velocity there, m, if we call that max there, v max. Now it tells you in the question that 35% of the weight of the child is the maximum friction, so we've got 0.35 mg there, equals mv squared over r. Let's just remove the max there, just to keep the page a little bit less cluttered. But can you remember, if you've got circular motion, there's your centre of your circle there, and that's distance r. That circumference around there, that's the distance travelled in one rotation is 2 pi r, isn't it? The distance travelled around the circle. So you can write velocity is distance travelled divided by time, and the time period is t there. So we can substitute that into here. So at this point you could pause the video at any point and try this yourself if you've sort of recognised you perhaps made a mistake. You know, you don't just need to keep sort of watching me, you could just pause at any point and keep try something out yourself. So I'm going to substitute into here. So mv squared, well v squared is going to be 2 squaring v there, so we're going to get 4, we're going to get pi squared, we're going to get r squared, we've got divided by t squared there and one of the r's, so that's going to cancel there like that, and that's going to be equal to 0.35 mg there like that. The m also cancels, doesn't it, like that. So we've got to there, so we can now rearrange to get t squared. So I've just rearranged there. So to get t there, you just move t squared up and shuffle things around, and you get t equals root 4 pi squared times r over 0.5 g, but r is 0.8 meters. Distance there, so you get 3 seconds as the minimum time. So we're on to the next one. State and explain how this time would change if a child of larger mass sat at the same place on the roundabout. Well, the centripetal force required would increase, wouldn't it? Because the centripetal force required is mv squared over r. So if you double the mass of the child, they would need twice as much force to stay in circular motion. But the frictional force is 35% of the weight of the child. The weight of the child would also double as well, so it would make no difference. And you can see that from here as well, can't you? T is independent of mass. So for the 2 marks, one of them is to say it would make no difference, and for the other one it's just giving a reason why, something along the lines of the centripetal force required depends on mass, the frictional force depends on mass, so both equations equally depend on mass, so the effect is going to cancel, or you could make reference to the equation or something like that. So you can check the mark scheme for the exact credit given, but that's also worth 2 marks there. Okay, so we're on to question 15. We've got a probe moving in space. Whilst moving, empty fuel tanks can be ejected by means of an explosion. This has the effect of increasing the speed of the probe. Discuss whether conservation of momentum and conservation of energy apply in this situation, and explain why the speed of the probe increases. Right, so we start off with conservation of momentum. So is momentum always conserved? Yes, if there's no external forces. So let's assume in this case in space there's no external force, so yes, momentum is conserved. So that gets us 1 mark there. A statement that conservation of momentum does apply. Ideally you'd put in brackets, since no external forces. It might be useful here just to have a little diagram. If you imagine there's a fuel tank on the right hand side and we've got some explosive here. This might be moving along in space at quite a high speed. This is sort of the before situation. If then you have an explosion, there's going to be a force this way, isn't there? And there's going to be an equal and opposite force on this empty fuel tank. Well, that's going to cause this one to accelerate. So if this is speed v here, the velocity of this now could be greater than v. It's speeding up because of the force. It doesn't ask us to discuss forces here. We need to discuss momentum and energy, but we could still have a bit of a discussion. So what's going to happen to this? Well, it may actually move backwards, or it may move just with a reduced speed. We don't know the mass in this particular case or the size of the force. I mean, we could just say it carries on moving in that direction with just a reduced velocity, or it could move backwards, you know. So that's going at a speed less than before, and we've got our explosion that's just occurred there. So let's take it with momentum first then. That's increased in velocity, hasn't it? So that's gained momentum. That's decreased in velocity, say. or even if it had moved backwards the other way, it still would have had a velocity change. So that's, say, had a positive velocity change, because it's, I mean, it depends which way you want to define positive and negative, but let's say that's gain momentum. That's going to have to have lost an equal amount of momentum, because momentum's conserved. If that's gained 1 million kilogram meters per second, that would have to have lost a kilogram meters per second. So that sort of raises there a couple of points. One, you can either speculate that the probe in the tank actually move in opposite directions, that the empty fuel tank does actually move backwards. It does say here move in opposite directions rather than have opposite velocity changes, but it may recognise that point that one has an increase in speed and the other has a decrease in speed. It's the idea that they have opposite velocity changes. But it does also say it will award a mark for the idea that the probe and tank experience equal and opposite forces. The key thing is that the probe and the tank experience equal changes in momentum. The magnitude of the change is equal. It's just equal and opposite. So ideally you would really say opposite as well. So that's 3 marks there relating to momentum. The other marks for conservation of energy, I mean, one easy mark is total energy is always conserved. You can never destroy energy, conservation of energy. So that's 1 mark. You're getting chemical energy, aren't you, converted into kinetic energy. Now, this could slow down, couldn't it? So that actually could lose, could have its kinetic energy reduced. This one is speeding up, it's going to have an increase in kinetic energy. But we know we've got this source of chemical energy, so that's going to have to gain more kinetic energy than this one loses. So in terms of the whole system, the kinetic energy of the whole system is increasing. So what we're looking for is that the total energy is conserved, the kinetic energy of the whole system increases. You've got to say of the system, not just specifically one part of it. And you need to make the point chemical energy is converted into kinetic energy. Okay, we're on to the next question. Just waiting for the camera to focus in here. Seems to be a little bit slow focusing. Right, a capacitor is charged by a battery as shown in the circuit. Calculate the EMF of the battery and the energy stored in the charged capacitor. So what have we got? We've got the charge on one plate, charge on the other plate, and we've got the capacitance somewhere. So just recognising the information you've got. Coulombs is a measure of charge, so we've got Q there, and that's our capacitance, farad, so we've got C. What's it asking for? The EMF of the battery, and it's asking for the energy stored in the capacitor. Well, what equations are relevant? We've got Q equals CV, haven't we, for starters? That's given to you on the back. Gives you it in the form C equals Q over V. So if we calculate V there, that's going to be the voltage across the capacitor. Is that going to give us the voltage of the battery? Remember, EMF just means voltage. Yeah, it will, because in this case the capacitor is fully charged, isn't it? So the voltage across the two is going to be the same. So if we just write V equals Q over C there. Now what do we use? Because we've got 2 charges here. Do we need to double it for Q? We don't, because when we talk about Q, the voltage stored on a capacitor, we mean the voltage that's being moved off one plate onto the other, so you don't double it. So it's 3.3 micro. So just remember micro is 10 to the minus 6 there, so we've got minus 6. And if we divide by the capacitance, 220 nano, what are we going to get? So let's just pause. So that's 15 volts there. 15 volts. So that's 2 of the marks if you check the mark scheme yourself. So now we're on to what's the energy stored in the capacitor. Well, if you look at the data sheet on the back, it does give you that. Now don't forget the half for the capacitor, so it's a half QV. So we've got a half, we've got our charge there, 3.3, times 10 to the minus 6, and we've got our voltage 15 there. So let's just calculate that there, and that gives us 2.5 times. Again, just finishing question 15, June 2015, 6pH04, used as the mock exam in January 2016. So just finishing off then, energy stored in a capacitor, 2.5 times 10 to the minus 5 joules. What we got on the next one? The capacitor is disconnected from the battery and discharged through a 20 mega ohm resistor there. Calculate the time taken for 80% of the charge on the capacitor to discharge through the resistor. The charge is Q, isn't it? And if we think about a QT graph, the initial charge there is 3.3 microcoulombs, and we're going to get exponential discharge, aren't we, like that? And we're after the time for 80% of the charge to discharge. You've got to be a little bit careful here, because if 80% discharges, that means there's 20% left, and in this equation here, Q equals Q naught e to the minus t over RC, that Q is the charge remaining on the capacitor. So that's going to be, we don't actually, I mean, we could use that initial charge there if we want. Remember, Q0 is the initial charge. You could work out 20% of that if you want and substitute that in there, but what's going to be left here is 0.2 of what you started with. So 0.2, 20% that is of the initial charge, is equal to Q0 e to the minus t over RC. So that's how we need to set things up, and you can see they cancel, so you don't actually need to, you don't even really need to know the initial charge, because this term here is basically equivalent to what fraction is remaining. Anyway, if you didn't get this previously, you could attempt to rearrange at this point now for t, couldn't you? So we're trying to solve both sides, so the opposite of E is ln, so ln both sides, ln of 0.2, ln of e to the minus t over RC, and the point of doing that, of course, was to get these two touching so they cancel. We're trying to solve for time, so we need to times by minus RC, so we get ln 0.2 times minus RC. Well, minus RC is minus 20 mega, 20 times 10 to the 6, I'm running out of space here. C was 220 nano, so in there we need the 220, and I've run out of space, so we'll just move the nano down there, times 10 to the minus 9 for nano, and that's going to give us our T, which comes to 7.1 seconds. 7.1 seconds. If you look at the mark scheme, you can see what the individual points were given for. 1 mark for recognising that there's 20% left, or you could have calculated that if you wanted to. If you'd got that wrong, you still get 1 mark for, you know, even if you'd used 80% left, you still get 1 mark for using that equation, but there is a mark for the final correct answer. So candidates who do use the sort of 80% idea, you can only score the second marking point there, so you're going to have lost 2 marks, so just be careful there in future. A little bit of a tricky question perhaps in the next one. Use an equation to explain whether the time taken for the capacitor to lose half its energy this time is greater or less than the time taken to lose half its charge. Well, can you remember the energy stored in a capacitor is half QV. Now, if it's lost half its charge, if it's lost times by a half, if it's lost half its charge, does that mean it's going to lose half its energy? Well, if it loses half its charge, can you remember Q equals CV? So V is Q over C. So if it loses half, half of its charge, if this halves here the charge, you're also going to half the voltage, aren't you? That's going to half as well. So when you've halved the charge and half the voltage, you'll only have a quarter of the energy left. So the energy is dropping at a higher rate than the charge and the voltage. So how does that help us? It said explain, use an equation, so we've got some equations here, to explain whether the time taken for the capacitor to lose half its energy is greater or less than the time taken to lose half its charge. Well, we've just said that the energy is decreasing at a greater rate than the charge. So if it's lost, it's going to lose its energy will halve in a shorter time, won't it? In less time than it takes to lose half its charge. You can see that from there. Look, if the time taken for it to is a certain time to lose half its charge, it'll have lost more than half its energy. So it's less of a time. I mean, if you wanted to, you could come up with an equation for it. We'll look at the Mark scheme in a minute, but Q equals Q naught e to the minus t over RC, V equals V naught e to the minus t over RC. So the energy stored is a half QV. If you times these two together and times by a half, you're going to get half the top line, which is Q naught e to the minus t over RC squared. E to the minus t over RC, and you're going to times it by that, so you're going to get half Q naught V naught times e to the minus t over RC all squared. So and that's going to give you the energy stored at a given moment in time, which is actually half of the initial energy. Look, W0 times e to the minus t over RC squared. So that gives you the energy stored at any given moment in time. So if you did plot an energy stored time graph, where that's your initial energy stored, after one time constant, it wouldn't be 37%, it'd be 37% of 37%, so it'd drop at a much steeper rate because of that square. I don't know off the top of my head what 37% of 37% is. You could calculate it if you wanted to. Now, that's worth 3 marks. If we actually have a look at the mark scheme, what you're going to get the mark for there. So 1 mark, I mean, there's different ways that might get interpreted, but what it's saying here is 1 mark for the idea of the energy stored is Q squared over 2C, or the energy stored is proportional to Q squared. Now, essentially, that's the kind of argument that I've made on the paper there, because if you take that V there, look, Q over C, you can substitute that in there. So you get W equals Q, V is Q over C, so if you times it by Q over C again, you're going to get Q squared over C. So these two are sort of equivalent to that, really. So you could have, sorry, losing the focus there for a minute, you could have written out all these two together. So the argument is use that equation there, and then, as I've said, if you halve Q, half times half is a quarter, isn't it? So you're actually going to quarter the energy stored. And I mean, I'm just reading out what it says here. Since the energy stored becomes a quarter in the time it takes for Q to halve, it'll take less time for the energy to halve. So something along those lines, but you're only going to get a mark for that. It's a dependent mark on either of these two, so you'd have had to have actually had some proof. You couldn't just sort of guess. You had to have, it did say use an equation, didn't it, in the question, so you had to have something along those lines there in order to get that mark. Or a reference to energy stored is half QV. Q and V both decrease over time, which is what I said, didn't it? I said Q decreases and V does, with reference to that equation over there. So I suppose this fits in with what I've said, reference to this one, and then an argument that V also decreases, and then similarly explaining that W will decrease at a faster rate, so it takes less time to halve. So a little bit tricky perhaps, that one, but if you maybe, but if you've seen the mark scheme there, hopefully that makes sense. The last bit then, D, student carries out an experiment to record data, so she can plot a graph of potential difference over time. What would be the advantages of using a data logger to log the voltage and a stopwatch? What would be the advantages of using a data logger rather than a voltmeter and a stopwatch? So when we say data logger, we mean basically a voltmeter connected to a PC. 2 marks, so we need to say 2 things. Well, if we just switch back over to here, I suppose the voltage graph would look similar, wouldn't it? If you had the voltage decreasing over time, obviously the initial voltage would be different, but it could drop quite rapidly. And if you were just if you just had a voltmeter there and a stopwatch, and you wanted to record your voltage and your time in a results table, you're going to have to look at the voltage, aren't you? Look at the time and then write them down. Obviously you can't simultaneously look at both immediately, so the voltage and the time might be changing as you look at the other one might be changing, so you're going to get a little bit of error there. And also it's going to take you time to write them down, so you're not going to be able to record them that rapidly. So it's those 2 points you need to make really. The idea that with a data logger you get synchronous readings, so you get the voltage and time recorded at the same time, or another way of saying it is the data logger records the readings at the exact time, or the point. Here, what does it say? The voltmeter and the stopwatch need 2 people, and the data logger needs only 1 person. I think it's making the argument there that if you had 2 people, maybe they'd be better at recording the voltage and the time at the same sort of synchronous point. I'm not sure about that, because you'd still need 2 people to communicate to each other how you were going to do it. You'd either have to say, right, let's write the voltage down when it gets to 3.53, but the other person recording the time would still have to look at the voltmeter. But anyway, I think that's a fairly clear point, that you get synchronous readings. The second one is you get more readings taken in a shorter time, or your higher sample rate, more samples, more measurements per second. So those are the marks that have been given there. Okay, over the page, and we're on to question 16. State Faraday's law of electromagnetic induction. So I guess you would start with the equation there. So it does say state the law. So I've written down that there. I think you'd have to define each of these terms. So you could say this is the induced EMF. Obviously that's quite an important word, induced, because it's about induction, it's about flux change and so on, isn't it? So the induced EMF minus, well, n's the number of coils, isn't it? So I mean, you can write this down yourself, n, number of coils. Delta phi is the flux change, and delta t is the time the flux change occurs in. This whole term there is the rate of flux change, isn't it? So in words you could have written this term here, you could have defined that to be the rate of flux change. So looking at the mark scheme, 1 mark for the induced EMF, quite important that. You could have said the induced EMF is proportional to the rate of flux change, if you've gone down the wordy route, or you could have written down the equation, but you'd have to define each symbol, which is what I was saying, n number of coils, phi flux, or flux change, depending on whether you've put the delta inside here or not, if that makes sense, and delta t. This is question 16b. The magnet is attached to the end of the spring as shown in the diagram. Copper ring, there's the magnet, there's the spring. Magnet's displaced vertically and released so it oscillates. Explain why this produces an alternating current in the copper ring. Well, this is about induction, isn't it? Part A was Faraday's law of electromagnetic induction, so it's going to be about an induced EMF, isn't it? So if you've got an alternating current, what comes before a current must be an EMF. So you're trying to explain why there's an EMF, but it's an alternating current, constantly changing direction, so there must be an alternating EMF, and it's an induced EMF as well. So you must therefore then be trying to explain why you've got an alternating induced EMF. You could picture the diagram like this. You've got the magnet above. In the question there, the South Pole is at the bottom there. So imagine the magnet was pushed up first on the spring. Excuse me, there's the South Pole, there's the North Pole. You've got the flux lines coming in there towards the South Pole and the coils down below. So this is a relatively low area of flux density. So the flux in the coil, the coils are going to be quite low. As you release the magnet and it starts to fall, just you can see here when the magnet's inside the coil, that's where you've got the highest flux density inside the magnet. So that's when the flux density is going to be its highest. And then down here, you've got the North Pole quite far below the magnet, below the coils now. And that's when you're going to get to a minimum again when the flux density is relatively small, so there's quite a small amount of flux there. It's just worth noting, look, that the flux lines are pointing up here when the magnet's above. They're still pointing up through the coil when the North Pole's below, so the flux is in the same direction there in both diagrams. So if you did want to draw a flux time graph, bit of a rough graph here, just trying to draw this at the same time as holding the camera. If you did want to draw a flux time graph, you can have a sort of minimum flux up here, and then as it oscillates, you're going to get to sort of a maximum and a minimum. Not necessarily going to be kind of a sine type graph or cos graph. I mean, obviously that's not cos or sine, but even if you lifted up a cos or sine, it's not necessarily a cosine type sine graph, but it's going to be something like that, isn't it? You're going to have a minimum here at position at the top, and when the magnet's at the bottom, that's when you get your minimums, and you get your maximums there when the magnet's passing through the coil. So what we're trying to explain, why you get an alternating current. Well, that's the previous question asked for Faraday's law, didn't it? Which relates the induced EMF to the flux change. Remember, this term here is the rate of flux change. So why do we get an EMF at all? Why do we get an induced EMF in the coils? It's because we've got a flux change, haven't we? As the magnet moves, the coil is in different regions of different flux density. So that's why we're getting a flux change there, because the magnet's moving. So that explains why we get an induced EMF. But why is it an alternating EMF? Well, if you think about this term, that's the rate of flux change. So if we look on the graph there, at that point there, at that point there, that point there, that point there, that point there, and so on. What property of this graph gives us the rate of flux change? It's the gradient, isn't it? Dθ by dt. Y-axis change over x-axis change, it's the gradient. So the rate of flux change, the gradient, is 0 at all these points. So that would be when you get an EMF of 0. So you could, if you wanted to, plot a graph below there of EMF versus time. And if we just did try and keep these graphs sort of synchronized, and we work down there, since the rate of flux change is 0 at those points, we'd get a 0 EMF. Here you've got a positive rate of flux change, haven't you? You've got a positive gradient, but since you've got a minus sign there in Faraday's law, if this term here is positive, we get a minus positive, so we get a minus, so you're going to get a negative EMF. Here we've got, as the magnet moves away from this midpoint, the flux inside the coil is decreasing. We've got a negative rate of change of flux. A negative is going to give us a positive. So without worrying about the exact sort of shape of this graph, it's going to look something like that, isn't it? So now we've explained why we get an alternating EMF. Sometimes the rate of flux change is positive, sometimes the rate of flux change is negative. So sometimes we get a negative EMF, sometimes we get a positive EMF. Now if we look at the actual mark scheme for that question, just to see how that breaks down, there's 4 key points. So the first one is the idea that the magnet is moving. So there is a changing field around the ring, there's a change in flux in the ring. The ring is experiencing different flux densities. That's the first point. Therefore an EMF is induced. That's the second point, so that's quite an easy mark. Third point is there's a change in direction of the magnet. Sometimes it's moving towards the coil, sometimes it's moving away. So therefore that changes the direction of the EMF. The fourth point is related to Faraday's law, that the magnitude of the EMF depends upon the rate of change of flux, and since the rate of change of flux depends on the position and the speed of the magnet, there's a mark awarded for the second point there. So that's the 4 points there. So the next question, just waiting for it to focus in there. The next question is question C. In question C it mentions the vertical component of magnetic flux density through the coil varies. If we just look at the diagram there, if we look at, in this particular case, look here, if we show this flux line there, it's sort of heading in this direction, isn't it? That flux line there has 2 components. It has a component in that direction there and a component in that direction there. So if we sort of imagine the pen as showing the horizontal component, that would be in this direction, and the pen there would show the vertical direction. And just refocusing back in there take a second. As the magnet moves, it's only the vertical flux which passes through the coil. Any flux in this direction, in the horizontal direction, would just pass above and below the coil. So it's only really the vertical flux change that we need to consider here. Calculate the maximum current in the ring. That's the maximum induced current. Well, if we write V equals IR, or in this case it's an induced voltage, so we can write induced EMF equals IR. So if we want the maximum current, we need the maximum induced voltage. Faraday's law gives that the maximum induced voltage would be minus N times the maximum rate of change of flux. Well, we've got the maximum rate of change of flux density, but that would be different to the maximum rate of change of flux. Can you remember that flux equals flux density times area? So if we substitute that into here, we're going to get that the EMF is minus N at change in BA over time. Well, area is constant, so we can just pull the area out there, and we've got this term here. But this term here, change in flux density over time, that's the rate of change of flux density which we've got there. So current is maximum EMF divided by resistance. So current is going to be maximum EMF here divided by resistance. So we've got minus NA over R times the rate of change of flux density. So now it's just a case of substituting everything in there. Number of coils, we need the number of coils, and the area is just going to be pi r squared. It's a circle. Resistance we're given the radius for pi r squared, and delta B over delta T we're given here. So if we look at the mark scheme and see how it's awarded the marks, 1 mark for use of area pi r squared, 1 mark for using EMF is BA over delta T. So we're taking the number of coils, taking N in this case to be 1, 1 use of I equals V over R, so it's given an answer of 4.1 amps, and the example of the calculations down below. Okay, on to a rather hazy question 17, hoping it's going to focus in shortly. It's asking for the unit of epsilon zero in base units. So anytime you're trying to find the unit of something, you need to rearrange. So moving that term up there, we're going to get Q1 Q2 over F for pi r squared. So we need to get epsilon zero there in base units. So the unit of charge is coulomb, so we get coulomb times coulomb, so we get coulomb squared. Force is newtons. 4 pi doesn't have a unit, and r squared, r's distance, so we get meters squared. Now, can you remember the base units? It's the meter, amp, second, Kelvin, and a kilogram. So the way I remember it is mass kg, where the A is the amp. So coulombs is not in amps, but we know 1 amp is a coulomb per second, if you remember, or you can get that from the data sheet, can't you? Current is charge over time, so amps is coulombs per second. So we want coulomb in terms of amps, so coulomb is going to be amp second. So if you rearrange that, coulomb is amp second. So coulomb squared is going to be amp squared second squared. So we've got amp squared second squared. So that's now in base units. Newton, well, that's force, isn't it? F equals ma. So Newton is kilogram for mass times acceleration, meters per second squared. So we've got kilogram meters per second squared times meters squared. So now we've got everything down to base units. Just need to tidy that up a little bit. So we've got amp squared. We've only got 1 kilogram there, so we're dividing. So that's per kilogram. We've got meters cubed there, we're dividing. So that's per meters cubed. And we've got second squared divided by per second squared. So that gives us second to the 4. So if you look on the mark scheme there, it's 1 mark for using for separately writing. It can't be implied, it needs to be a separate statement. 1 mark for showing that the Newton is equivalent to kilogram meters per second squared. 1 mark for showing that the coulomb is equivalent to the amp second, and then 1 mark there for the correct answer. So we've got a question: electric fields are caused both by point charges and by parallel plates with a potential difference of voltage across them. Describe the difference between the electric field caused by a point charge and the electric field between the parallel plates. Your answer should include a diagram of each type of field and a reference to electric field strength. So here's a point charge. It could be positive, it could be negative. I'm going to draw it positive. There's our two parallel plates there, and if we apply voltage between the two parallel plates, let's pop a cell on there like that. So that's the positive terminal, that's the negative terminal. So we've got a positive plate and a negative plate. So the electric field around a point charge is radial. I think you have to draw a minimum of 4 lines like that, so each line should be 90 degrees apart. If you're going to do more lines, you have to be careful because the lines have to be equally spaced. If they're not, and you have to use a ruler, but I'm holding my phone at the same time, so I can't. The direction of the field lines indicate the direction of force on a positive charge nearby, so a positive charge would be repelled, so you want those lines pointing away from a positive charge. If you remember, you get a uniform field between two parallel plates. I think it's a minimum of 3 lines, but the spacing does have to be, they have to be equally spaced. Again, you should use a ruler. Mine is close to being equally spaced. You won't be holding a phone when you draw yours, so you'll find it a little bit easier. A positive charge here would experience a force in that direction, so it should look like that. So we've done the diagram. We still need to make a reference to the electric field strength. The equation for the electric field strength around a point charge, a charge of a single point, is kq over r squared. Well, you can see from the diagram, as r, the distance increases, you can see the spacing of the lines gets further apart, so the electric field strength is going to decrease. If you quote the equation there, you can see when you double r, that's going to get squared and become 4, so the electric field strength will get 4 times smaller. So that's an inverse square law. The electric field between two parallel plates is E equals V over D, where D is the distance there between the two plates, and V is the applied voltage. So you can see that's constant, isn't it? For a given V and D, the electric field strength between two plates is constant regardless of where you are in between the two plates. So, I mean, you can look at the mark scheme yourself. For parallel plates, it's looking for a minimum of 3 parallel, equally spaced lines must be touching the plates. For the point charge, a minimum of 4 equally spaced radial lines touching the charge point in the middle. The directions of the fields must be correct for both diagrams, consistent with the charges labelled. So if you'd drawn a negative charge in the middle there, a positive charge would have been attracted in, so these arrows would have been in the other direction. If you'd reversed the battery, the polarity of the battery there, these arrows would have had to have reversed direction as well. And the comment there, parallel plate, you need to say the field strength the same at all points, and for a point charge you can either say the field strength decreases with increasing distance, or you can make the further point that it obeys an inverse square law. If you double the distance, you'll quarter the electric field strength. Okay then, on to question C. 2 small spheres, L and M, attached to non-conducting threads. They have to be non-conducting because these spheres are going to be charged. You don't want discharge occurring along the threads. Suspended from a point P. Each sphere in this case has got equal charge, and it's given you the charge. And the spheres, question 17 C. 2 small spheres, L and M, attached to non-conducting threads, suspended from a point P. Each sphere given an equal positive charge of this amount here, so they're repelling each other, so that's why they're both displaced by that angle there, and they're hanging in equilibrium, so they're not oscillating around or anything like that, they're stationary. Non-conducting threads, so no discharge occurring along the threads off from the pivot point, so they're remaining constantly charged. Each sphere's got that mass. So by considering the forces on one of the spheres, calculate the tension in the thread and the angle. So let's start with the free body diagram then. We can pick either of these. Let's start with M. So there's our free body diagram, there's M. So we've got our tension acting along here. So there's the vertical, dotted line on there. So we know that's angle theta. So that's our tension. We've got the weight acting downwards as well. So weight, let's just call that mg. Remember, we've been given the mass. And we've also got repulsion, haven't they? They're both positively charged. So we've got some repulsion. Remember, that's the electrostatic force acting in that direction there. Now, we're also told they're hanging in equilibrium, so the net resultant force of these three is 0. So at this point, there's two ways you could approach the diagram. One of them, one approach you could use is, since these forces are equilibrium and the resultant force is 0, these forces will form a closed force triangle. So if you've got the tension acting in this direction, you can start with any force. I'll start with the tension. If then you add, like a head to tail method, if you add the weight coming down there, the weight mg there, and that's angle theta to the vertical, then the electrostatic force, it must take us back to the beginning there. That's the electrostatic force there. Because remember, when you do a resultant force diagram, if you've gone from there to there to there to there, you've essentially stayed at the same point. So that's a resultant force of 0. So you could do that approach. I'll do the other approach later. So once you've done that, you can find these two sides of the triangle. Then you can find t and theta, which is what the question is: calculate the tension and the angle. So we know mg because we've got the mass, 2.7 up there. So let's say we start with theta. If we wanted to calculate theta first, we can write tan theta. Remember, SOHCAHTOA, it's opposite over adjacent, so it'd be F over mg. Now the force is the electrostatic force between these two objects, which is going to be K Q1 Q2 over the separation distance squared, all over mg. And we know all of these things. K is 8. If you remember the Coulomb constant, 8.99 times 10 to the 9. That's given on the data sheet at the back. Each has a charge of 4 times 10 to the minus 7. So we need to square that because we're timesing them together. It's not times by 2. It's squared. 4 times 10 to the minus 7 times 4 times 10 to the minus 7 is 4 times 10 to the minus 7 squared, not 4 times 10 to the minus 7 times 2. Divided by the separation distance squared, 0.25 centimeters squared there. And then let's put a big bracket around that there. And then all over mg. Remember, the standard unit of mass is the kilogram. So 2.7 grams is 2.7 times 10 to the minus 3 kilograms times 9.81. And then if you calculate all that there, that'll be tan theta. So to get theta, it's the inverse tan. Make sure your calculator is in degrees mode if you're going to give your answer in degrees, and just do the inverse tan and you can find theta. So that's what I've just done. Tan theta to 3 significant figures is 0.869. Calculating degrees mode, theta inverse tan of that comes to 41.0 degrees. So we found theta. It also asked us to find the tension. I've found theta first. You might have found the tension first and then found theta after. There's different ways you could do it. If you take your pick with SOHCAHTOA, there's lots of different ways of doing it. I mean, you could use Pythagoras' theorem, couldn't you? Because you're just looking at the triangle there. Or now you've got the adjacent and the opposite, you could use cos or you could use sine. Second way to do it, you'll see some writings appeared here. We'll just go through the second way of doing it, which probably most of you have done, I'm guessing, which is to consider vertical and horizontal. So you take your tension, resolve horizontally, so part of that tension is pulling horizontally, so that's going to balance the repulsion force, because you know the spheres aren't moving, so you've got balanced horizontal and vertical forces, and part of the tension is pulling vertically, and that's going to balance the downwards weight. So starting with the horizontal, this is opposite the angle, so if you think about it, t sine theta gives you the horizontal component, and that balances the repulsion, which we said earlier, if you use Coulomb's law, is K Q1 Q2 over r squared, and t cos theta gives you the vertical component. That's going to balance the weight, so get mg. So we've got two simultaneous equations. If you remember, tan theta is sine theta over cos theta, so if you divide here and here, since that's equal to that and that's equal to that, that left side divided by that is going to be equal to that divided by that. So the divide t sine theta by t cos theta, you get sine over cos, which is tan. So you get tan theta on the left hand side equals this divided by this. So you're going to get k q1 q2 over r squared all over mg, which is what we got before. Probably requires a little bit more thought, a little bit more effort doing it this way. If you can, remember to consider a closed force triangle when the resultant force is zero, when you're in a balanced forces situation. I think it just makes it a little bit easier. So both methods are going to give you the same answer for theta, and once you have theta, you can either work out t by considering that closed triangle, or once you've got theta here, you can go back into any of these equations. Once you've got theta, you've got all the terms except t, so you can find the tension. So if finally, if you look at the mark scheme, essentially there's two different approaches that we've taught through. The top approach, well, both approaches, if you've tried to use Coulomb's law, gets you a mark. Calculating the weight gets you a mark, and then you either resolve vertically and horizontally. You need to do both to get one mark, or you essentially follow the approach where you do the closed forces triangle, which is the second method. So if you attempt to combine the components to give you tan theta, that's going to get you a mark, and then it's a mark for both of the correct answers for theta and t. In the second scenario, you can use Pythagoras to find the tension force, because remember it's a closed triangle there, and there's also a mark in the second attempt along here. And that's it. I'm not going to do question 18. I'll let you look through the mark scheme yourself there. I hope you've got a good score.